So I left you hanging in the last video about considering what it means. We had been using and calculating approximate area underneath some sort of function by using what we call this Riemann sum right here. Okay, and in that what we would be doing is finding heights of rectangles and then the widths of rectangles and then adding up all of those rectangles as they moved along the x-axis. So we had to determine a c sub I, a delta x, and then take the sum of all of it. Alright, now what we're going to be doing is the exact area underneath the curve. So this is what I want you to consider. Instead of choosing, in the last example, we chose an n. We chose a number to divide the overall interval into. So we're going to still look at this function f of x equals 3 times x over the interval from 0 to 6. And where before we chose n equals 3, so we would take this interval, whoops, sorry, bad line, and we would divide it into 3 equal sections, therefore our widths, the widths of these rectangles that we, in this case I'm using the circumscribed rectangles, were just 2. The widths were 2. Alright, but what I want you to consider now is, what if we chose something higher? What if we let n equal, say for instance, 12? Okay, well then I'm going to be taking these and dividing them even more. Alright, so what I have now are 12 equal in width rectangles. And I'm going to go ahead and do the circumscribed again, so I'm going to be using, in this case, my right hand sides of these lines to kind of dictate the height of these rectangles. And here's what I would have as these rectangles. Notice this whole rectangle, we would have to figure out, alright, what is the width and what is the height? So we would be having to figure out what is f of c sub I. C sub I are just these x values that are occurring at each one of these points. And then our delta x, we mentioned delta x is determined by, what that was it was our upper minus our lower limit over n. Okay, so what I want you to realize is, yes, there's still some excess here in all of these rectangles that we've drawn, but it's a lot less excess that's being done here when we have made these rectangles into smaller widths. So what I want you to understand is, the larger we let n be, the smaller in width these rectangles get. We're using the same setup, that same Riemann sum, but this time we're not going to choose a value for n. We're going to choose n to be infinity, essentially, and that's where we're going to have to throw in this limit. So let me now show you how this is going to work, and what you're going to find is you're going to be using those skills that you developed in 6.2 when you were working with limits of these summation notations. We're going to be using those now in this section. So when I want to find the area underneath this function, this is what I would do. So the first thing I'm going to have to determine is, what is delta x? So the upper minus the lower and all over n. And this time we're just going to have to leave n because we're not setting n equal to anything. So it's just going to be, oops, sorry, my lower was 0. It's just going to be 6 over n. Okay, so here I go. I have the limit as n approaches infinity of the sum, I equals 1 up until n, of f of, now here I am just going to use my right hand sides of these rectangles. So I'm going to go ahead and let c sub I equal my delta x times I. So this is a little bit confusing, but what my delta x is, what I've determined it to be, is 6 over n. I have taken this interval length and I've separated to n what we'll eventually see is a million little pieces, and then times I. So my f of c sub I is going to be 3 times 6i over n, and then times my delta x, which is, as we determined, 6 over n. Okay, so now what this is right here, these are the heights of all those rectangles, and this is the width of all those rectangles. And there's an infinite many rectangles, so that's what's a little bit strange about this. So I'm going to go ahead and just solve this. What you're going to see here are all of our 6.2 concepts of summation notation and formulas and properties coming into play. 0, so what we get in the end is 54. I just want to say that in that PowerPoint, what I really set us up for was understanding how you set up the Riemann sums, and then eventually we were building to getting to that point of we're going to have to calculate the limit of Riemann sums now with n approaching infinity. So that's going to be how we are going to exactly discover the area underneath the curve. And the reason why, once again, is if we can draw rectangles, inscribed or circumscribed, it doesn't matter. If we can draw rectangles within a bounded region, what we're hoping to see is if we can get them infinitesimally small, that's going to get us the exact area under the curve. So here is just that visual of this again. So and it goes kind of fast, but here it is one more time. Those are inscribed rectangles, and we're dividing that bounded interval into smaller and smaller portions until hey, you know, those rectangles get us exactly that area underneath that curve. Okay, so we're going to go ahead and jump right into the problems that are going to be using. Not only can we set up these limits of Riemann sums, but also can we solve them. So we're going to be combining all of this new information that we've learned in chapter 6.2 together. So what we're going to be looking at is this function right here, and it says use the limit process to find the area, and there's a little bit more in your book that says we need to find the area of the region between the graph of the function and the x-axis over the indicated interval. And then it also says to sketch the graph. So I'm going to first sketch the graph so that we have a visual of what we're doing here. This is a quadratic, all right, and I'm sorry, and then the interval that they specify is from 0 to 1. So I'm going to go ahead and sketch this. Alright, so this is a parabola, being that it is a quadratic. All it is a quadratic that's been shifted up 2. So instead of making the vertex appear on the 0, 0, it's going to be up at the 2 mark. And then it's going to go over 1, up 1. And then normally we would know that it would go over 2, up 4, so it would be somewhere way up here. So here is kind of that outline. But all we're interested in is the area underneath our curve, and it stops from the 0 to 1 interval. So this right here is what we're trying to find. So the thing is, what we could do is start to divide this 0 to 1 interval into as many little teeny tiny pieces as we could. We could kind of pick an amount and then start drawing rectangles, but the idea is we're not going to pick anymore. We're going to let n go towards infinity. And then so this would be f of c sub I. We're going to have to determine what our c sub i's are that we're going to be plugging into our function to find the heights. And then we're also going to have to determine a delta x. So delta x, once again, how you find that, it's our b minus our a, so 1 minus 0, all over how many pieces are we separating this into? Well, we're not fixing it at any certain amount. We're going to leave that open because we're going to let that number that we're dividing this interval into be towards infinity. So what we have is our delta x is equal to 1 over n. And just because I'm more comfortable for c sub I, I'm going to go ahead and let c sub I equal delta x times I. So in other words, 1 over n times I. Okay. Alright, so this is my final setup. I'm going to have the limit, alright, of the sum from 1 to n. And here I'm going to plug in, here's my c sub I that I determined right there. I'm going to plug that in to my function. So it's going to be I over n squared plus 2. This would be the equation that would get me the height of all my rectangles. And then so that's just this piece right here. And then I'm going to multiply that by delta x, which we determined was 1 over n. Alright, so this right here is the whole entire setup. This right there would get you some points on your test on just being able to set up the limits of this Riemann sum that would get you the total area underneath a bounded curve. So now it's just going to be solving this, and here's where I'm going to start to simplify this all out, and eventually I'm going to, just like what we did in that first assignment from 6.2, we're going to be solving this out. So I'm going to have the limit, and I'm going to go ahead and distribute this 2 to the top and bottom of that fraction. It's I squared over n squared. And I'm going to go ahead and distribute this in. What we get is, okay, so that's just me distributing this in. Okay, and yellow is kind of bright. I'm going to choose a different color. Alright, and the next thing of business is you can take, remember, this summation notation and distribute it to each one of these. So I'm going to go ahead and do that now. We have the limit as n approaches infinity of the sum. Okay, so what this all amounts to is the limit as n approaches infinity. And what I'm going to go ahead and do is break this I apart from this n cubed, this division of n cubed, so I'm going to rewrite it like this. And then plus the sum. What I hope you can see is revisiting what we learned in the past video with calculating out the summation notation. This right here, as we have this index variable I, that's only going to affect this I squared. So I'm going to pull this out as a constant and then just calculate the sum of I squared. So what we get is the limit, okay, and then plus, here, this technically is a constant too, so I'm going to pull this out front, 2 over n, and then I equals 1 to n, and this is just going to be 1. Okay, so chew on that for a while. This right here can be subbed out. Remember, we had those properties, and it's stated that if you have the sum of some sort of index variable only being squared, what this is all equal to is 2n cubed. Okay, so this right here is going to be going in for that summation notation. So we're going to get the limit as n approaches infinity of 1 over n cubed times, now this is out, this is in, 2n cubed plus 3n squared plus n all over 6. And then the rule for some sort of constant that's you're taking the sum of, this would just be 1 times and then our top number, which is just n, so it's going to be 2 over n times just n, because it's 1 times n. Okay, so now I'm going to simplify this all out. Top will stay the same, but then what we're going to get is 6n cubed, and then plus these actually cancel out, and what we're going to get is 2. Alright, so now here's where, going back to old ideas of limits, the limit can also kind of distribute to each one term by term. So I'm going to be analyzing this right here. We have a rational function going on, and we're trying to find out what is the limit of this rational function as n approaches infinity. Well, if you will look back to your 5.7 sections, what this is going to entail is just you using that one method where you find the highest degree power on the bottom and you divide everything by that. So what this amounts to is 8. And then what I just want you to recognize here is, remember, we're studying the limit as n approaches infinity of the function 2. So if you were just to look at a function, and I mean this is just f of x equals 2, it's forever just at 2. What is y doing is this n approaches infinity. Well, as we go further out, it's always just going to be 2. So that's one of your old properties. If you ever are studying the limit of a constant, it's just going to be that constant. So now what I can go in and do is finally plug in infinities if you so chose to do. But the idea is we have that property that we're able to state these are going towards 0. So what we get is 2/6 plus 2. So in other words, 2 1/3, and your book may simplify that to be 7/3. Done. So what I want us to kind of see is right here, this area of our square would have been around 2. All right, so that seems pretty reasonable. The area is 2 there. And then according to our calculations that we just did, this area would be about 1/3. So 2 and 1/3 is the area underneath that curve.